Hi, I'm James McGuire, and on today's Tech Voices, we're talking with the co-founder of a company I find really interesting. The company is called Vinci. It's an AI startup, and it's a pioneer of physics-based AI. They specialize in hardware design and simulation. Very cool stuff. And to talk about the company, I'm joined by Hardik Kabaria, co-founder and CEO of Vinci. Hardik, really good to have you with us today.
Well, thanks for having me.
We've got some company news to talk about. We'll get to that in a minute. But first, let's get a brief overview of the company. You've said that Vinci does for physics what large language models do for language. That's pretty interesting. What does this mean in terms of real world use cases?
Yeah, let's start there. Where is physics and where is it used in real world use cases? We'll start for something very simple. Today, all the hardware companies in the world, they create products. The products that we like, other enterprises use, and this is a $4 trillion worth of economy. That's how much hardware is created
Wow.
and sold every year.
Okay.
But think about how many people are designing and understanding and analyzing it. Is extremely small number of people of the planet, best in millions, and they're using legacy tools that were been around for tens, not 50, 40 years
Hmm.
to understand the performance and manufacturability of these parts. Now, how does that problem become complex? We are creating more and more complex and high resolution manufacturing process. Like you are a nanometer, single digit nanometer in semiconductor,
Hmm.
micron, submicron in electronics. But the system we are designing keeps getting bigger and more complex. So take a step back. We are designing more complex hardware with high fidelity manufacturing processes, while we all care about understanding physics. How is this part going to do heat transfer? Where is going to be my hotspot? Is it going to bend and deform in a manner that it won't create a reliability problem? All of those are a physics problem that
Hmm.
we haven't updated the stack or haven't created a capability that makes it accessible to everybody. That's where we strike. So
Hmm.
we are creating a physics reasoning layer. What does it mean? That means once our software is deployed, anybody in the hardware engineering org can ask this question. Hey, what would be the performance of my design for thermal, for various physical scenarios, and it is accessible to everybody in the company, as well as across the different stages of your program, be it at the architectural level all the way to post-production, right?
Hmm.
And now what they can achieve is they can achieve an answers with guaranteed accuracy because physics is constant. So we always provide answers that are rooted in the first principle physics equations. And we do it faster in a manner that is automated, and you can achieve the simulation or results at the same level your manufacturing process is at. For whatever resolution your manufacturing process is at, you can now perform analysis. So that's the capability we are deploying.
Uh-huh. Well, it's a world that is very exacting in terms of the engineering. Like, 1/100th of an inch makes all the difference in the world. Correct?
Exactly. So the accuracy and the resolution both are extremely important to the users because in hardware, you care about being precise and
Hmm.
you care about understanding the tolerances of any decisions you are going to make.
Interesting. So, there's company news today. Vinci has launched its second core physics capability, thermomechanical simulation that predicts warpage and hardware designs. What type of companies will use this, and what will they really do with it?
So let's start by understanding what warpage is.
Please,
So
please
today,
explain that to me as a layman. Right.
let's start from understanding the problem, right? So in semiconductor and electronics, both of these worlds, we are creating more complex designs, be it at the component level, like DRAM, be it at the chip packages level, that to GPU, CPU, or all the way to printed circuit boards. So now you have boards, electronic boards, where you have GPU, CPU, ASIC sitting on it. And because of the complexity and heterogeneous material, these parts deform due to thermal loading. This is what is known as warpage. So what? It creates reliability problems as well as manufacturability problems. So now these companies, whether you think about fabless all the way to advanced packaging ecosystem, to companies that design boards, to electronic manufacturing service provider, So the whole ecosystem is interested in understanding at any given phase in design how much my design is going to default, how much stress, mechanical stress is going to create on various parts of my chip package or copper wires or boards. And is it going to break? Is
Hmm.
it going to create reliability issue? Or is it not at all manufacturable altogether? That's the type of physical performance analysis this model will enable. And that also gives you an idea to the potential users of this product feature.
Hmm. Okay. Well, the thing I find really interesting is that, in language AI, hallucination is tolerated. In fact, it's pretty commonplace. But in hardware, an hallucination melts phones, possibly. So, how do you guarantee determinism in a system that incorporates AI?
Yes, so let's go all the way to basics. Today, often AI is used for creative start. That's where it began, text or images.
Hmm.
And physics, as we've been talking through, is a lot more deterministic. And
Right.
it enables very specific decisions that could have non-trivial impact on the outcome, whether creating a better product or just like you said, creating something that heats up a lot and ends up throttling the product.
Hmm.
So when we started creating our product, we went to the basics. We created AI that understands the physical equations or the laws of physics, first principles, ground up. So the AI we are creating is not a fine tuning of a language model. It is the model that grounds up, understands laws of physics.
Hmm.
Or to an engineers, I would say a heat transfer is governed by a partial differential equation, what we studied in undergrad and grad school. We are teaching that to the AI. It's ground up, understands the physics. And we use these models to produce the answer for partial differential equation. At the time our software is deployed. When our software is deployed, it's behind the firewall. So that means any particular company's, design files, layout, material properties, how they are planning to use these chips, those are secretive information known as IP. That IP will never cross the firewall. So they can be safe and secure about the things that are secretive to them, but they can still get the answers to the laws of physics or analyzing physical part performance behaviors. And that's the product we provide.
Aha. Well, let me ask the question in a related way. So, if Vinci's process is truly deterministic and solver grade, what exactly is the AI doing? I mean, where does learning end and numerical method begin?
Oh, and that's sort of the core of our product. So let's dive in. Like I said before, we created AI that truly understands the physical equation or the underlying phenomenon. So at the time of usage, a user will give us geometry, some design file, material properties, or what we call boundary condition, or how the part is going to be um, used in some environment. And now you want to perform an analysis. The AI model will predict the solution of partial differential equation. And then it will also orchestrate all the way to converging the solution for a specific physical phenomena. So it takes care of the fact that this is the laws of physics somebody's trying to analyze. I'm going to provide a solution for that. And then it goes to the next step of actually making sure it's converged result. So yes, it's solver grade. We always provide the answer that is rooted into partial differential equation. And we use AI to get to the answer faster. So what is the benefit? The benefit is that you can get answers really fast, orders of magnitude faster. Now you can run extremely high fidelity analysis. You can really resolve nanometer level features on a centimeter meter scale domains, right? You don't have to train your model. We have done the job. We have trained it. So when we deploy, you start using it. Why? Laws of physics are universal, right? And then the last piece is it gives scalability because now you don't have to worry about defeaturing or simplifying or pre-processing your problem. You just drag and drop your design files and say, okay, I want to simulate it. I want to analyze it.
So really, the model cannot hallucinate.
Now, our product will always give you answers that are rooted into solving partial differential equation.
Mhm. Interesting. All right, well, the other thing I think is really interesting is that we've seen AI transform content and code and images and graphics, but What fundamentally changes when AI begins reasoning about matter and heat and stress and material failure? What's going on there?
So first, just think about where does this go, right? Today, analysis of physical performance is a chokehold. Can only happen with a high caliber talent on a set of software that doesn't run at the speed the design can be changed. So if you give this capability, we see that our customers start running a lot of different iterations. So that's a very good starting point that we end up creating advantage. More iterations, more analysis, hypothesis, you'll end up creating better product faster.
Hmm.
So that's the first order effect. The second order effect is now you will actually push the analysis to a higher fidelity. You will actually perform analysis that resolve your manufacturing processes nanometer to centimeter. And now you will create more interesting insight, the insight that you couldn't get to before. That will enable your design team to create a better product. And at the end, that's our goal. Our goal is to create a tool that enables our customers to create better hardware product faster.
Hmm. Hmm. Interesting. Um, and I'd love to get your sense of how this is going to play out for the teams that are actually using it. I mean, does physics intelligence compress the design cycle because you can design so much faster, or does it actually expand ambition, allow engineers to do all sorts of things that they previously thought were too risky to even try?
So it's definitely doing the first part. Like I said, because we have made it easier to do perform analysis, and we
Hmm.
also made it more accessible. So you don't have to spend a lot of time prepping the performance analysis. Rather, you just drag and drop design file at any given stages of your, program.
Hmm.
So yes, it's definitely creating more iterations. And but I'm actually happily surprised about the second part. It's actually leading to higher ambition as well because now they are all striving towards more unique insight. Or can we create this insight earlier stages in my program? Not do this sequentially, like do design, perform analysis, check manufacturability, and run the loop, right? And
Hmm.
this loop can be days, weeks, months long. Instead, they want to bring physics into the enough for physics analysis into the design cycle at every stage. That creates higher ambition, right? So we are seeing both into the deployments we have across industry.
Hmm. Makes sense. Hardik, that's a lot of good stuff. Anything you want to add about Vinci and where you're going with the company?
I mean, like simply put, our goal is to make physics performance analysis accessible to everybody
Hmm.
at any given stages of your hardware program. And you can still use our product with the same level of security that our customers care about. That means, hey, I want to protect my design data. I want to protect the type of things that are secret about me, but that secrecy shouldn't be hold the rate at which you improve your design, or like you said, the ambition you create.
Hmm.
And this proof point that we don't have to train anything or just use out of the box deterministic, those proof points have been validated by, more than half of leading semiconductor companies on benchmark examples.
Hmm.
So that's the place where we are at today, and our goal is to make this accessible to everybody who are pursuing ambitious hardware programs.
Great. Hardik, thank you so much. I learned a ton for sure, and I hope we speak again sometime. Thank you.
Thank you. Thanks for having me. Appreciate it.